right, so today we will talk about we'll continue talking about graph problems. Specifically, we'll talk about network flows and something called maximum flow problem, which means getting as much stuff through as possible through some sort of pipes. That will be our goal. We'll start with some slightly simpler problems, such as something called bipartite graph problem or bipartite matching. It's also known as a marriage problem or student assignment problem, also a very popular problem. And then we'll discuss another graph problem, which is sort of in between these problems. So let's start with bipartite matching. I can't pronounce this. So again, I'll use my favorite paint to explain this, right? So we will have a little bit of, again, you have a graph, and we have a set of vertices. 1 second. Oh. Okay, super. Okay, super. Sorry about that. This is money. Okay, that's good. All right. Yeah. So, all right. So we're talking about a set of vertices or nodes, if you will, right? And the key part is these are. I will put like maybe let's do 4 on each side, right? And we'll basically and the key point is that they are disjoint or basically sort of like right. So again, men, women, or I don't know, husband, wife, or maybe students and internships, things like that, right? Left side, right side. So basically the goal is to match, right? So I will use some. So this will be maybe Alice, Bob, right? And this will be what Carol, and this will be what Dave probably, right? And these will be like Acme Corporation, right? And this will be what will be big company, Boeing, not a very good company to work for, right? So let's see, it would be what? Cat, Caterpillar, right? Right, Cat, and what's D? Yeah, Cat, and D company? D. Dodge? No, Dodge is not company, it's the name, Mark. Deutsche Bank. Okay, very good. Okay, excellent. Deutsche. Now they have to spell it. I can't spell.
Yeah, you just can't put DB.
DB. Let's do DB. Okay, that's good enough. Or DN's business, but Deutsche Bank. Okay, right. So the point is now, right? We have these. So obviously Alice cannot go work for Bob, right? And Acme is not going to hire Boeing, right? But these are internships, right? And the key point is that some companies are willing to take anybody, well, pretty much, right, maybe, and some are very selective, right? So we will take the case of the easy case that Dave, right, like Dave has an awesome match with Deutsche Bank, and that's it, right? So Dave only works for Deutsche Bank, right? That's all he dreamed about his whole life, and Deutsche Bank says, okay, Dave, you are the right person to do this, and that's it basically. So this is an easy case, right? But now let's look at some other cases, right? So let's look at Alice. Maybe has a possibility of working with Acme. That's okay, right? And Carol has a work with Cat, right? However, unfortunately, for Bob, Boeing does not want him, right? So he has a problem, but not all is lost. I'll use different color. I'll use maybe possibilities like, so Bob could work for Caterpillar, and I guess Carol could work for Acme. And let's see, do we need anything else? And Alice could also work for Boeing, right? And again, so can we fix it? So the red represents the current status, right? Assignments, right? And of course, the goal is to optimize the number of job assignments, right? So I'll use something called hospital assignments. They use this in a hospital assignment problem, right? You have practicants, pretty much anywhere we have internships or jobs, basically, right? And you need to assign something. So let's see. Could we actually imagine? Well, I can see from the green one. So green assignments would solve the problem, right? Alice could work for Boeing, right? Bob would work for Caterpillar, and Carol could work at Acme, right? Or Acme, right? So how do we, assuming we have our present state is red, right? How do we find? So we have these are edges, obviously, right? Representing, you could have a weight of 1, represents a connection, basically, right? There's no weight, or weight is just a unit, basically. So some sort of iterative process, right? So iterative improvement, basically, what we could do is basically if we find a so-called augmenting path, basically an improvement, we basically do it basically, right? So that's the idea for this approach. So in this particular case, how could it work, right? Obviously, Dave and Deutsche Bank, they're in good shape, right? They have perfect matching. They won't be affected by this algorithm, right? So idea is, of course, is you have to consider you need to build a path basically, right? From Alice to Boeing, right? You go through, you check, right, step by step, see if you make an improvement basically, if you can adjust the augment the path basically, right? So again, so of course in real life is this going to be a very easy process, right? If how it is in real life, if you say, okay, I want to work for a different company, right? There's usually some tension, some friction in real life, right? You can't just say, okay, I'm going to quit, or I'm not going to take your offer. I have a better offer I'm going to check some other offers, right? Usually both sides, have a play a little bit, right? So let's see, maybe we can do a little AI assisted decoding. Maybe we can do this. Let's try, see if the algorithm works actually. So let me go to my GitHub. See if I can do it from scratch. I don't know. Oh, I can't spell today. What's wrong with this also? The lost password problem. Alright, that will work. No. Okay. Authentication. Oh, come on. $8.40. Too many repositories. Alright. So topics, we'll call it bipartite matching. Tough one to say. Bipartite matching. Kernel. Alright. Bipartite matching. Matching problem isn't. So we want to, so some examples, like I said, so some real life examples of this problem. Jobs to workers, like we talked about. Course to students, of course, right? Only one course allowed. What else? Again, marriage, right? Of course, task to machines. right? Assuming, right, with some limitations, right, and so on and so on, right? And maybe one more. Come on, one more. I guess not. Rooms to guests, right? So again, if some rooms, there's some basic idea is that if you're in a hotel, right, maybe some guests have really strong aversion to certain rooms, and some people are willing to take any room available, basically, right? So, and some rooms you don't want to give, maybe the best rooms there's certain guests you don't want to give the best room to, maybe, right? So certainly, right? So let's see about some basic one. Well, let's see if we have any. We'll see about this one, maybe. So let's make a function. So let's represent. Okay. So first, how would we represent our bipartite graphs? Since let's use something simple. Let's use simply a list of numbers for both sides, right? Since we know each side has the same number of nodes, right? No, so each side would have a list of same length, right? So right. So for example, same length. So for example, yeah, I guess we could do this. I suppose that would be one way. That would be one way of doing it, or we could do also 0, 1 on other side. Maybe I'll make this a little bit bigger. You can see this idea. So that's the basic issue: is how we represent this type of problem, right? Or maybe we can make it more universal. Maybe make it ABC, right? On let's use maybe the preferences, right? Maybe it's ABC. Let's allow strings, maybe, right? Numeric seems like kind of easier, right? In IDs, basically, right? And then you have maybe somewhere you have a sort of lookup for the actual names, maybe, right? That'd be also a possibility, right? I prefer actually to use separate graph, but I guess this would work, right? Let's try this one first, right? And then see if that doesn't work, right? So then to represent edges, we could have this, right? List of tuples, right? So edge meaning so each edge represents a connection, meaning connection, a possible connection, right? Right. Possible connection between node on the left side and the node on the right side. That would be one way of doing it, I guess, right? Right. So it makes sense, right? Are you with me so far? Yes. Or more or less? More or less, right? And now it's morning, and so we have our graph set up, and then basically, yeah. I guess adjacency matrix, but let's not do matrix. But let's not for now. Not for now. All right. So, yeah. So we have that would be basically edges. Let's see, for I in range. This would be basically left side, right side. Is this actually going to be useful? Let me think now. We have two loops, right? We can of course use a combination, so this basically gets you all possible connections, right? But of course then if you get all possible edges, then you just assign, you just take the first assignment and there's not going to be any difference, right? So that's not really useful, right? So I guess we'll do edge list, right? So possible connections, right? That's not really good, I guess, right? So input to solve or bipartite would be a list of edges, right? Right, list of edges basically, right? That's the easiest, right? With each edge represented as tuple, this edge would represent one possible connection between node on the left side and node on the right side. Okay, all right, okay. So, again, yeah. So we already talked about this, right? So, all right. So in comes right? List of edges on represent list of tuples, list of edges, represent list of tuples, represent the matching. Okay, but that's of course it's going to be. Well, let's see what's happened. Yeah, okay. No, two edges shares node on the left side. Okay, that's fine. Okay, so define. Looks like this AI today is really sleepy too, I guess. So get matching. Bipartite matching. On, I guess we could, yeah, edge is basically right. Left, right is edge, right? Much left, much right, right. And the thing is, of course, here, I guess, left side, left nodes, right node. Let's make it easier for the AI. AI is basically, we'll do this by your hand, basically, right? Because I could calculate it, right? So, greedily we'll add an edge, right? It doesn't share it, right? Yeah, let's take a look. So matching, we have set, right nodes and set, right? So we have two set and we start building it up, basically, right? We assume all edges, of course, again, assumption is all edges, edges are, I guess I'll write here like this. Oops. Edges represent all possible, yeah, and only, right? Yeah, all right. That I think makes sense, right? And we're going to return a list of edges that represent matching, the maximum matching, right? Okay, so we have set, empty set, matching, right? That's our solution basically, right? Let's start going, right? So hopefully there's going to be a loop, right? For edge and edges, right? If left node, right node, edge, right? Obviously, on if left node not in left nodes matching, right node not in right nodes is matching, right? So we can do it, right, safely. So this is an extremely greedy approach, right? We just keep going, we take the first available matching, like first job that comes our way, right? So that's going to give you an optimal solution? No, right? Because it's just this is just the first step, right? Because this is our first matching, right? This will be our first step, right? First step, right? Well, no, first step. Well, sort edges on the left. No, we could do that afterwards. Let's or first greedy matching, right? Well, yeah, right. Afterwards, right? So this will, okay. So this will not be a complete solution, right? Obviously, right? This will just be a first solution, right? A solution which is not going to be optimal. Obviously, not up to what to do, right? Make iterative improvements to the matching, right? So we have some, because we have some matching, yeah, okay, that will be next. But for now, let's test it. Let's see what we have. Let's have our function. Let's see if this is going to work. Alice, Bob, Carol, right? Can we? So this is actually, we can give names now, right? So left side is Alice, Bob, Charlie. No. Charlie, this David Eves. There's going to be some modern marriage thing, but no. But Carol on Dave, right? Since to keep is our example. Left side Dave, right? Right side is Acme, Boeing, right? Caterpillar. How the heck does it know that we're going to use Caterpillar, right? That's cat, right? Very good, right? And Delta instead Deutsche Bank. Deutsche Bank, right? Very nice. All right. So, and I guess I'll make it easier. Since I don't want to type, I'll just use cat, right? I'll use cat for short, right? On DB, right? Because I don't want to keep typing this, right? So we have possible, holding edges. So Alice Acme, right? That's correct. Yep. Alice Boeing. No, Bob Boeing. Well, Bob would love to, but he's not going to work for Boeing, right? So Alice Boeing, right? Bob is not going to Boeing cat, right? Carol, yeah, Bob only gets one choice, right? Alice and Carol, they have choice, right? So Carol, Acme or cat, right? Carol is Acme. Carol is also cat, right? And Dave, of course, is going to Deutsche Bank, right? We already know that, right? That's set in stone. Okay, let's see how the function. So test it. Let's test it, right? So edges, right? Alice, Acme, right? That looks good. And we have our left side, Alice, Bob, Carol, Dave, and right nodes, Carol, Acme. So let's see how this works, right? So should I turn Alice, right? Let's see, Alice, Acme, right? Bob, Cat, and Dave, DB, right? Let's take a look. Get greedy. I guess I'll call it greedy matching, right? But I guess we'll improve it, right? Yeah, exactly. Of course, not shocking, right? Greedy first approach, right? Is not gonna be the optimal one, right? So we need to make iterative improvements. Let's see if we can do anything better, right? Again, always, can we do better, right? So get some sort of solution, right? If two people, one person gets a job, that's better than no job at all, right? But we still want to do it better afterwards, right? So let's see if we can do iterative improvements right here, right? So let's see if this approach works, right? Again, this is right. Yeah. Okay. Let's do this. So let's see if this actually works. AI is actually stuck right now. Can we do any better? We could sort, I guess, but it might going to be actually not. Let's iterate. Yeah. Come on. This AI is completely lost. For what? Let's see if this is going to help anywhere. Let's see if this works. For X len matching, right? Len matching, right? Right. Let's see. Right. We can try. Okay. Let's take a look. Right. On if continue. Okay. Right. So this is going to be one improvement. Let's see if this works for length in matching. We keep trying through all our nodes, right? Do we need the I actually? I wonder if this, I don't like this approach here, by the way, right? This is kind of smells unPythonic, right? This range. This looks like something out of C code, right? Or C++ code, right? So this is a little, it might work. It looks okay, right? Left node matching or right node matching. Right, I would use something. I'll probably refactor this once this actually gets to working. But what we are doing, this is interesting. So it looks like if you make a single improvement, right? If you make it looks like this. We keep trying an improvement, meaning this loop will run. How is this going to work? It will keep running if it doesn't have any improvement, basically, right? If left node matching or right. So basically, if you don't have an improvement, then basically we make single improvement. Let's see if this actually works, right? So I'll print the matching, right? Verbose, I'll add this here. Verbose, my favorite flag. Verbose is false, right? And if verbose, right? Yeah, we have a solution here. If verbose, right? If verbose, right? We print matching, initial matching. Now we can see now that our greedy approach, we can try to improve it, right? Let's see if this works. I don't know. This loop is kind of little sus, but I don't know. We'll see a little bit, right? A little bit. Okay, and we didn't have. Oh, right. Looks like we didn't get any improvement at all, actually, right? And I'll do verbose true, right? Verbose true. Oh, there we go. Verbose true, right? Verbose true. Let's see. Yeah, initial matching. So this loop is not really does not look very very promising because it looks like we tried to check what happened here. We had the matching. If left node in matching, in left nodes in matching, right? Where are they? Okay, in a set, right? Or right node in matching and right nodes in matching. Basically, this group is not going to do anything, right? Because we know they are in the matching set already, right? Yeah. So how this actually, because we know at least one of them will be matching already, right? So that's not going to be a very good improvement, right? We still need to rewrite this, right? Or we could just see if actually, but of course the whole idea is we iterate over these possibilities. So we need to basically we want to augment the past. Basically, we want to add something, right, while keeping the previous, without going down, right? You don't want to have just a new matching, have a new match but lose the old match, and so it's even, right? We want to keep increasing it, right? So here this does not look like it. This looks like what? If one of them basically looks like this code is basically going to run loop through all of the matchings basically, and will not do anything, right? This is kind of useless code basically. It's like because we guarantee that this will be true. That's the problem with AI, right? It's not. So if edge in matching, well, obviously this, and also I think even here is if we get the edge, right? Oh, no, okay, oh, never mind. No, this is good. Okay, so if we can only improve the matching if the edge is not already in the matching. Well, yeah, no, basically if it's already, because we have a current edge, right? We're going through, okay, right, obviously. Right, okay, we're going through edges of all possibilities, right? We're basically looking at we're looking at moves, right? We're looking at moves, right? And see, so this first, okay, this makes sense, right? So this makes sense, right? This first one, right? Because obviously if you only have this move, we're not gonna consider adding because we already have it, right? So, but this part here is the one I'm kind of have an issue, right? Because we have this set of matching nodes, right? We need to, this is not gonna, or maybe and, right? Let's see. Because let's look at situation, right? We have Alice, right? We check Alice and Boeing, right? A possibility of this, right? If we add Alice to Boeing, right? We can consider, okay, because we're gonna find it, right? Okay, here's Alice and Boeing, right? On the bless someone. All right. So we'll need to consider. Okay, assuming Boeing is not taken, right? Obviously, so I would assume this would have to be and, right? If both are already matched, right? Like we're looking at maybe Carol going to Acme possibly, right? So this is really, looks like this is one I don't think, this is going to basically, right now currently this means it will make it loop through, right? So this is kind of, I'm going to leave it off actually, right? So, right, for now I'm leaving it off. I am leaving this off since, yeah, right, now, and assumes again, Alice Boeing, so we need to find somebody to go to Acme. Then if Alice goes to Boeing, right, then Carol has to go to Acme, right, and then Bob has to go to Cat, right, and that I guess would work, right? So basically, to have a chain, right, so it's kind of like looking at the past, right? So kind of, well, not very good algorithm. But again, so we consider possibility with I would say backtracking perhaps a little bit, right? So we try to find put this edge. We have somebody, either one of sides is not assigned yet, right? We try to find the matching, say, okay, this is possible improvement. Again, Carol and Acme, well, that would be a harder case, even though this is part of the solution, right? But we need at least, we know obviously, I think the approach is that we need at least one of these edges, right, of this, is going to have to be, new, right, not used before, right, one of the nodes, right, because otherwise there's no point checking maybe Carol Cat, right, maybe everybody has already, everybody's matching and everything is good, right, but yeah, if you see there's somebody not being used, it's Bob or Boeing, right, one side or other side, right, there's possibility of improvement, right, that's when you start looking, basically, right. So I think so we'll do that. So if both, right, we'll continue, right, so we'll leave this and, right, crucial difference. So right, yeah, now the question is, how do we do this? We find, right, so this means here, right, so at this point we have an edge that is not in matching on at least one node, yeah, is not in matching, right? So if both are not in matching, it's easy, but of course our greedy approach we have found it, right, if we had just complete unmatching, right? So yeah, if both are not in matching, right, then we can safely add, right? Yeah, and that's it, right? Easy case, yeah. Right, now this is the hard one. How are we going to solve this one? Now the hard case where one of the nodes is already in matching, right? And that means we have to find a replacement, right? Right, let's take a look. For I, right, and I don't know, is it gonna work, right? So let's see, this is very, let's see, so matching left, matching right, okay, we have the edge, if left node in left C, I don't know, this is a little bit suspicious because I would imagine, remember, okay, so I find Alice Boeing. Okay, I find the replacement, right? We need to find two. So Alice goes to Boeing. We have a match, but this means Acme, right, does not have an employee, right? So we have to find the replacement, right? This means we find Carol, right? And to me, this looks like this code stops there, right? It stops here. It finds the next one, right? So, but then of course we don't really have an improvement, right? We are still stuck there. But the question is that okay? Possibly, maybe that's enough, right? If you do randomly, right? Well, then, because Bob will eventually reach an agreement with Cat next time, maybe, right? That's a possibility, right? Easy case. I'm not so 100% sure, right? We just basically means like we make a replacement without losing anything, right? I would prefer to actually try going into depth, right? Try finding it next, right? Again, this is just a really naive sort of almost brute force approach, right? But again, the purpose of this is, of course, is that you get the idea that we are a replacement. Because in the next part of lecture, what we'll be doing is maximum flow, right? We'll be doing these augmentations, so to say, right? So I guess we should take a break, right? I'll run the program once, right? So we'll leave continue at 10. Oh, we got it, right.